Good afternoon and welcome to the final installment of our Traffic Safety Virtual Series, brought to you through a collaboration between the New Hampshire Office of Highway Safety, Dan Goodman with AAA of Northern New England, and Chelsea Mastoni with the Injury Prevention Center with Children's Hospital at Dartmouth. My name is Jennifer and I'll be the moderator for today's panel discussion about vehicle technology, but before I welcome in our presenters, I'd like to go over a few housekeeping items with all of you. First, if you are looking for a certificate of attendance and you're a driver's ed professional, you can follow up with Chelsea. All other professionals can follow up with me. We'll have our contact information located in the chat box to the right of your computer screen. And speaking of the chat box, you cannot interact with the panelists, unfortunately, directly, but you can send us questions or comments that you might have that may come up during any of these presentations. And Chelsea, myself, and Dan can field those questions and comments and hopefully get those to the panelists during our Q&A session at the end. So please feel free to do that. And lastly, we do have a post-event survey that will pop up as you exit the session. We encourage all of you to take that survey to let us know how today's session went and if you have any comments or anything that you would like to see for future webinars. We appreciate that. So without further ado, I'd like to introduce our panelists today. Joining us is Mike Allen with 3M, Matthew Lum with the American Automobile Association, and Mike Marshall with MLM Diagnostics. Welcome, everyone. At this point, I'm going to give the presentation over to Mike Allen, who will be our first presenter. Let me do that. You should have the presentation rights, Mike. Mike Allen is a senior government transportation safety specialist with 3M and is the ATSA New England Chapter Technical Chair for Pavement Markings and has done extensive training through workshops for transportation agencies and local LTAP training centers. He has been with 3M for 15 years, currently covering New Hampshire, Massachusetts, and Maine. He has a bachelor's degree in marketing from the University of Connecticut and a web certification from Merrimack College. Mike, welcome.
Thank you, Jennifer. Thank you for having me. Thank you, Jennifer. Thank you, Dan Goodman from AAA for inviting me, and look forward to this discussion today for improving road safety with wet reflective pavement markings. So as I introduce our topic here, as I start up, really kind of give you a little background about 3M and what we're doing. 3M technology improves the visibility of roadway infrastructure in several different areas. I work for 3M Transportation Safety Division, and this division focuses on retroreflective signing, like you see on the left, pavement markings like you see in the middle, and temporary traffic control like you see pictured on the right. And these three segments make up the market that we primarily serve. So history of roadway safety. I would like to kind of give a background in where we are at as far as automated driving systems. And when we look at some of the technologies that 3M has come up with, you know, as we're the first to show wet reflective pavement markings, really visibility, providing that visibility and guidance at night, in the rain, and at dawn and dusk, really through wet reflective markings, through fluorescent sheeting, and really providing us now the visibility that we need to provide safety to drivers day and night. So the vehicles that we're talking about here today, as we talk about automated driving systems, 3M is working with automotive OEMs, automotive suppliers, component manufacturers, and DOTs to develop safe solutions for the future of our roadways. So obviously safety is only the beginning. The core of our Connected Roads mission is really to bring everyone home safely. We're pursuing a future of zero deaths on the road, but there are a variety of other advantages to building simple, redundant infrastructure to support the vehicles of tomorrow. So a lot of the technologies that I'm talking about today, really, it's a redundant technology that while they provide safety to us in the future, they continue to show us today and provide that visibility and reflectivity that make things safer, make our roads safer. So for example, as we look at the technologies, you know, automated vehicles could potentially, in the future, reduce 80 to 90% of accidents caused by human error, right? Give us greater capacity to put smaller lanes in. I'm out of southern New Hampshire, and in New England, there's a lot of focus on complete streets, and complete streets are really to make the roads smaller and give greater pedestrian refuge. So that greater lane capacity could come from some of these technologies. Increased efficiencies and better flow through the intersections. There's been a lot of pedestrian fatalities, as we all know, and complete streets and a lot of the low-cost safety improvements that some of the local agencies and state agencies are implementing are really being used to reduce these fatalities and make our roads safer. So by 2023, 71% of all of our new cars should have the lane departure warning systems. And there's a lot of technologies on a car. I'm not going to talk about a lot of them today. I am going to talk about lane departure warning a little bit because of the increase that we're seeing across the world in this technology. I have a Toyota Sienna that has basically a camera behind the rear view mirror, and it looks at everything in front of me, and it uses that technology to tell me when I'm veering out of lanes and I'm traveling where I shouldn't. So what are some of the things that the existing challenges that are out there that we're looking at that we need to mitigate? Right now, that camera that's on the top of my Toyota Sienna is primarily looking at the markings, and it's visibly looking for what's on the road. So as a traffic safety professional, we are focused on providing good, durable pavement markings. What a lot of people are familiar with is paint, which is primarily what a lot of states have used in the past to provide markings on the road. But paint in most states is not considered a durable marking. And when you go to remove markings, like you see in the picture, scarification makes it difficult to see where the lines were. Or in the middle, you can see pictures of crack seal. When crack seal is put down these roads, sometimes the crack seal is put right on the seam of the asphalt where the skips, where the edge lines, where the white and yellow lines are, and that makes it difficult for not only you and I to see the line, both day and night, dry or wet, but for the vehicles to see where that line is. So it's important that we specify basic information with states and locals to put those lines off of the edge, off of the seams of the asphalt when the new asphalt goes down, like you see on the picture halfway to the right of the screen. And then really to specify ways to show the vehicle, the cameras, the ability to see the markings better. And the marking on the bottom, the preformed tape that has the white in the middle and the black on the outsides, that is a marking that is very visible to camera because it has high contrast. And I'll talk a little bit more about that as we go into the presentation. So as I said, pavement markings must be visible both day and night. What we see during the day is the pigmentation, the white, the titanium dioxide of the color, the whiteness of the marking. We don't see reflectivity during the day. We primarily see that at night when the light source from our car hits the optic in the pavement marking and comes back to our eyes, that 20-meter geometry. So driving at night in the rain is a big problem. And in 2017, about 7,000 people died in the U.S., died in crashes on United States roads when it was raining. 55% of those deaths occurred at night or in low light conditions. And only 25% of travel occurs at night. So why do wet reflective pavement markings matter? This is these are three pictures from the same intersection, same location. And this is what the driver sees. So when you're behind the wheel, you're looking to the left at a daytime dry pavement marking. At night, you're looking at the dry reflective pavement marking at night with the light source back to your eyes, and then to the right, nighttime in a wet and rainy situation. And as you can see, that visibility decreases when you go to wet and rainy. So what happens when pavement marking materials disappear? Obviously it provides reduced visibility, not only to you and I, but to the vehicle. The vehicle cannot see the line, so it cannot help you make decisions. Increased discomfort, obviously, for the driver, less effective lane guidance for the machine, and increased crash risk. So studies were done, and I'll talk about two specific studies here, one with the Federal Highway that talked about evaluating wet reflective markings to help reduce crashes. And as you can see, the crash modification factors were assigned to the study. 46% reduction in run-off-the-road crashes in multi-lane roads, 41% reduction in crashes with injury on multi-lane roads, and 12% reduction in crashes with injury on freeways. So really this study was done in a cold weather state, with the exception of North Carolina, Minnesota, and Wisconsin. Like New England, the study indicated that wet reflective pavement markings reduced that number of total crashes, injury crashes, run-off-the-road crashes, wet road crashes, nighttime crashes, and nighttime wet road crashes. So that reduction of injury crashes was statistically significant. And after analyzing the data, the researchers determined that the benefit-cost ratio for multi-lane roads is 5.44, and the benefit-to-cost ratio for freeways is 1.45. So these are pretty significant. This is the first time that we've seen Federal Highway and crash modification factors and benefit-to-cost ratios assigned at a very high level to wet reflectivity. Another study that was done by the Texas A&M Transportation Institute, who do a lot of pavement marking studies, is safety effects of wet weather pavement markings. And they found a 32% reduction in wet night crashes and a 49% reduction in wet night fatalities when they looked at wet reflectivity. So why and what is different about wet reflective pavement markings? So let me show you a short video.
Are visible in steel conditions, but how effective are they in the dark? Newly installed markings with 1.5 index glass beads offer initially acceptable retroreflectivity. Under dry conditions, markings with 1.9 index microcrystalline ceramic beads are more effective than 1.5 index optics. Optics with microcrystalline ceramic beads also retain retroreflective performance over longer periods of time, on average, than conventional glass beads. However, when markings with 1.5 or 1.9 index optics are covered with water, most of the light that should be returned is instead scattered, making pavement markings difficult to see in rainy conditions. Optics with 2.4 microcrystalline ceramic beads from 3M provide true wet retroreflectivity. To help enhance safety and visibility for people and automated vehicles, these markings work with water, providing excellent light return in wet or dry conditions. Providing pavement markings that offer excellent retroreflectivity, day or night, wet or dry, is how we're helping bring families home safely. Newly applied.
So optics in the pavement markings return that light back toward its source. And what you're seeing here is a picture of both wet reflective optics and glass beads. The larger ones are composite optics that are the color of the marking, the white or the yellow, and then the glass beads, which are clear, and they are used for reflectivity as well. When we talk about wet reflectivity, when light travels from air into water, the direction changes. This is called refraction. And you can see it in this picture. Whenever you put the pencil in a glass of water, you can see the refraction of the light. So it doesn't give a clear line. 1.5 refractive index glass beads are commonly used for dry conditions. But what happens when they get covered with water is they basically don't send light back to that driver. So 1.9 index refraction glass beads or composites, they do still fail in wet and rainy conditions, but they are more durable. And more durable means longer lasting, more visible pavement markings. Lastly, 2.4 index glass beads are very useful to return light in rainy conditions. They are very durable as well, and they provide wet reflectivity. So our products have a combination of wet and dry refractive index optics, and these are used to provide a pavement marking solution. So what are some of the specification considerations that agencies would use to make their roads more visible today and tomorrow for the cameras of the future? In general, improving these visibility of these markings makes them more visible for human and machine systems. Minimally need to include the presence of the marking on the road. Consistency obviously is important, and that consistency is being looked at from the MUTCD right now. There are many recommendations that are being looked at through Federal Register as the new MUTCD is being evaluated. There's a lot of considerations to go from a 4-inch line to a 6-inch line across the country. That's one thing to consider. Lane markings often include optical elements, the visible optics that provide the visibility at night. The combination of dry glass beads and dry and wet elements in a double drop liquid would give you maximum visibility and durability of your roads. And for the most part, these products are recessed. They're put in a recess below the surface to provide more durability and protection from the plows. Contrast markings, like I showed you in that tape in the beginning, that have the white in the middle or the yellow in the middle and the black on the outsides, they provide more visibility on light-colored pavement, specifically concrete. We don't have a lot of concrete in New England, but down in the middle of the country, there's a lot of concrete. There's a lot of contrast tape and contrast markings that are used to provide visibility not only to humans, but obviously to machines. And lane demarkings and dimensions and performance are not uniform, so you want to specify performance in your contracts. So these automated vehicles rely on the sharp contrast between the luminance of the marking and the luminance of its immediate background to detect that pavement marking. So the more visible, the more contrast that you can provide either through a contrast marking or through a product that is continually visible, the better your markings are going to be and the safer they're going to be. Poor pavement markings, adverse weather conditions, and glare do interfere with continuous automated vehicle operation and require that special consideration. Consistent dimensions and geometries are helpful and appropriate metrics to ensure markings are effective. And if you have a maintenance program and an asset management program as an agency, you can adequately update your markings and consider a minimum level of reflectivity. The two considerations in your specification that most states use to provide that minimum level of reflectivity is both wet continuous and wet recovery. These are ASTM specifications like you can see, and there are ASTM test methods that can be used to provide performance when a contractor installs the product on the road, so the agency can have the assurance that they're getting the product that they're paying for. And in addition to these two components, the ASTM Wet Continuous E2832 and the Wet Recovery ASTM E2177, ASTM 1710 is a dry component, and most of our states in New England, Massachusetts, Rhode Island, Maine, New Hampshire, Vermont have that minimum level of both dry and wet reflectivity. And these are the test methods that you could use to achieve those results. One study that's being done in combination with Texas A&M through Minnesota Department of Transportation is looking at the durability and longevity and standards for wet reflectivity in pavement markings. And they are looking to determine the driver's needs, the wet reflective values, the dry reflective values, to implement statewide markings that are visible to both humans and machine. So these are the products that 3M primarily uses to provide visibility to both machine and humans, whether it be the elements in the glass beads that you see that go in a liquid on the road in a recess, whether it be the tape, the durable tape like you see in the middle that goes in a recess, that can be done standard or with contrast markings to be more visible to vehicles, or temporary tape that you see in work zones. In work zones, vehicles can veer very easily, especially at night. When you go into a work zone, there's a lot of attention to speed, and when you go into a work zone at night and there's a shift in the roadway, and all of a sudden the markings disappear or they're grinding up old markings, we call ghost markings, and ghost lines will actually move you in the direction that you probably shouldn't be going in. So a wet reflective temporary tape, like you see here on the right, will provide that delineation to both humans and machines. So as we wrap up, key takeaways. Rain and light conditions are aggravating factors in crash risk. So you want to help to mitigate those with a good solid specification. At night during rainy conditions, non-wet reflective markings cannot be seen. And those are primarily small glass beads, ASHTO type 1 through 4. They don't have much dry reflectivity typically. Recent research links wet reflective pavement markings to helping reducing crashes, as I showed in those two studies. Not all pavement marking optics have the same performance capabilities. 2.4 refractive index optics do provide optimal light return during rainy conditions at night, and obviously some visibility during the day with our dry 1.4, 1.9 index glass optics. And then wet continuous method, ASTM 2832, is ideal for when you compare the 2832 wet continuous versus wet recovery. Wet continuous is visibility in the middle of a rainstorm. So that's when you're going to need it the most. When it's straight out raining like crazy, like cats and dogs, as they say, you want to be able to see that line wherever you're going. Wet continuous will give you that specification. And we have additional research coming from TTI and Minnesota DOT to set those visibility standards. With that being said, are there any questions?
Thank you, Mike. I don't see any questions at this point, but we should have questions at the end of the presentations. So we'll have those ready for you. But I just wanted to make one comment on your presentation. At one point, you talked about how humans can often interpret what's real, can machines? And I think that question summarizes kind of where we're at with vehicle technology right now. Lane departure is here, that technology is here, but it's interesting to see the connection between wet pavement markings and the other products that 3M puts out to machine vision systems and how they operate safely. So that's just an interesting thing to think about. So I appreciate your presentation. Thank you.
Thank you, Jennifer.
You're welcome. So at this point, I am going to introduce our next speaker. And while I do that, I'm going to give you the presentation, Matthew. I'd like to welcome in Matthew Lum. Matthew is an automotive technical engineer at the American Automobile Association with a bachelor's degree from North Carolina State University and a master's degree from the University of Central Florida. He joined AAA in 2015 and has led a diverse range of research projects, some of which include electric vehicle range and efficiency, pedestrian detection, and active driving assistance, and that's just to name a few. Matthew also served in the United States Coast Guard and has been published in SAE technical papers. So at this point, Matthew, the floor is all yours.
Thank you, Jennifer. Yeah. Sorry, get this slideshow in front of me. Okay. Is the slideshow up for everybody?
Yes, I can see that.
Okay, perfect. Thank you for that introduction, Jennifer. As she said, I am an engineer here at AAA, and we, over the past couple of years, have been doing multiple research projects and a variety of topics relating to new vehicle technology. We do this for a couple of reasons, mainly to educate consumers on the proper operation of these systems, as well as to provide industry with constructive feedback on further development of these ADAS systems. Specifically in this context, we have looked at all kinds of systems such as blind spot warnings, automatic emergency braking, active parking assistance, lane departure, and more recently, automatic emergency braking with pedestrian detection and active driving assistance systems, otherwise known as SAE Level 2 driving assistance systems. Those two, the AEB with pedestrian detection as well as the ADA evaluations, are going to be the focus of my discussion today. So jumping right into this, we evaluated both of these ADAS systems in a variety of scenarios with both on the closed course as well as in naturalistic environments with respect to our active driving assistance evaluations. Specifically, before we go into that, into more detail with both of these evaluations, we started this research with a couple of goals at hand, specifically to challenge these systems to see how they perform more with edge case scenarios that drivers will typically encounter in everyday life, in addition to some of the more standard test methodologies that you would find defined in either Euro NCAP or some IIHS tests, for example. Specifically with pedestrian detection systems, we evaluated them on the closed course with both adult and child pedestrian dummies. For the adult pedestrian targets, we evaluated them in a variety of situations, such as a more standard perpendicular adult crossing scenario, as you see in the picture on the left of the presentation. Specifically, that just emulates an adult walking into the travel lane in front of an approaching vehicle. Besides that more standard test, which is replicated by other safety organizations, we kind of pushed the envelope with a few other scenarios, such as having a pedestrian crossing an adjacent street as a vehicle is making a right turn. So think about like a downtown area of any major city, for example, where let's say a vehicle has a green light to proceed either straight through an intersection or make a right turn. So while a vehicle could be making a right turn, a pedestrian could also be simultaneously crossing on that adjacent street because he or she has a walk signal as well. So we evaluated that specific situation, as well as nighttime testing as well. And besides the adult scenarios, we also did a test with a child pedestrian dummy, which the child target emerges from between two parked vehicles in the path of an oncoming vehicle. Most of the tests were conducted at 20 and 30 miles an hour, which are reasonable speeds that you would encounter in a typical urban or neighborhood environment. Moving forward to the active driving assistance testing, this project evaluated the test vehicles both on the closed course and on a naturalistic highway environment. Specifically on the closed course, we looked at a few different scenarios, such as the lane keeping performance on a straight road with well-defined lane markers, as you can see on the picture on the right of the presentation. Those lane markers were freshly painted within a few months prior to the actual testing. A few other scenarios evaluated in the closed course include a simulated disabled vehicle halfway in the travel lane, once again illustrated by that picture on the right. So specifically for this, we used a soft car, which emulates all the characteristics of a real vehicle in terms of radar signature, LiDAR signature, and any infrared characteristics as well, to make sure that the soft car is as realistic as possible to a real vehicle in terms of the sensors that are commonly placed on today's vehicles. In addition to that disabled vehicle scenario, we also evaluated the stop and go functionality of these ADA systems. So think of a typical traffic jam on an interstate where traffic stops momentarily and then picks back up to about 15, 20 miles an hour or so and then stops again. We evaluated the performance of the ADA systems in that context as well. And for the naturalistic evaluations on for this, we covered about 4,000 miles approximately between all the test vehicles. We drove them from Los Angeles to San Francisco on both Highway 101 as well as Interstate 5 going back to Los Angeles. So with the 5 test vehicles that we had in the project, the round trip was about 800 miles. So you add that up between the 5 test vehicles, that's where the approximately 4,000 miles of driving comes in. So going into some of the specifics with these projects, starting off with pedestrian detection. Let me replay the video. This is a standard test with the adult crossing into the travel lane as the vehicle is approaching. This particular video clip here, the test vehicle was moving at 20 miles per hour. And this is a pretty standard Euro NCAP test in which the pedestrian will make contact with the target vehicle at 50%. So 50% offset would basically be where the emblem is on the vehicle there, assuming that no speed reduction is affected by the test vehicle. So for this test, the vehicle successfully recognized a pedestrian crossing and avoided contact. For this more standard test, at 20 miles an hour, one test vehicle, such as the Toyota Camry pictured here, avoided contact for all 5 test runs, as well as the Honda Accord test vehicle also was successful at avoiding collisions with this particular speed. However, at the higher speed of 30 miles an hour, all test vehicles made contact with the pedestrian dummy at least once, and for the collisions that occurred, a minimal amount of speed reduction was noted. This right here illustrates the scenario with the child pedestrian emerging from between the 2 parked vehicles here. This speed was once again 20 miles an hour for the test vehicle. This test is very challenging for the systems because the pedestrian is not visible until immediately before impact, such as maybe about 2 seconds or so before the vehicle reached the area where the pedestrian is. So unfortunately, the test vehicles were much less successful with this scenario, with collisions occurring for both 20 and 30 miles an hour. This right here illustrates the scenario in which a pedestrian is crossing on an adjacent street as a vehicle is making a right turn. This test was extremely challenging because for all test vehicles evaluated for this project, not a single collision was avoided for any of the test vehicles. And this test speed was 15 miles per hour. So it's assumed that vehicles had a very difficult time with this evaluation because the field of view for the cameras placed behind the rear view camera or rear view mirror is not able to detect the pedestrian right up until impact. So with some industry briefings that we've held at the conclusion of this project, we were informed by a lot of the automakers that were included in this testing that this specific scenario is being addressed in future versions of pedestrian detection systems. And lastly, with pedestrian detection, we thought it would be prudent to evaluate these systems at night because approximately 3/4 of pedestrian fatalities occur at nighttime, low lighting conditions such as this. For this test, this is also challenging because there is no street lighting on this particular testing area. However, we think that this is still appropriate to evaluate because a lot of residential areas throughout the country do not have good street lighting present. So this test speed was a little bit slower than the 30 miles an hour that we used previously. All vehicles were evaluated at 20 miles an hour for this particular test, and not a single collision was avoided for any of the test vehicles. So moving on to our most recent research project with active driving assistance systems, we evaluated a number of mid-size SUVs, or mid-size and large SUVs, excuse me, such as the Kia Telluride, BMW X7, a Subaru Outback crossover, a Ford Edge crossover, and additionally, we included a Cadillac CT6. While the CT6 is not classified as either a crossover or SUV, we thought that it would be good to include it nonetheless because of the Super Cruise system. Super Cruise is unique in that it allows hands-free driving as long as the driver is looking at the roadway ahead. As you might be aware, Super Cruise is limited to geo-mapped interstates and highways. So this is another unique feature of Super Cruise in that it is not able to be engaged outside of those geo-fenced interstates. So because of that, the CT6 was not able to be evaluated on the closed course, but it was included with the naturalistic testing. All testing was conducted at Gomentum Station in the Bay Area. This facility is great for autonomous vehicle testing and ADAS system testing because there are approximately 23 miles of roadways available within the facility for a range of scenarios. So this specific test is a simulated disabled vehicle. So for AAA, this type of scenario is extremely is of extreme interest to us because AAA handles approximately 30 million roadside events per year, with roadside technicians finding themselves on the side of busy highways at literally all times of the day. So typically when a disabled vehicle is partially obstructing a travel lane, it is more common for the vehicle to only be somewhat in the roadway, such as having a rear quarter panel, for example, sticking out into the roadway versus how we placed the vehicle here, where it was such that exactly half of the vehicle was in the roadway. We did this to give the ADA systems as much opportunity as possible to pick up the disabled vehicle ahead and either slow or stop completely. For this test, the test vehicles were approaching at a speed of 30 miles an hour. This speed is a little slow in the context of typical highway environments where speed limits are around 55 miles an hour or higher. However, from a practical sense, we did not evaluate at that speed simply because while the soft car is made out of foam, significant vehicle damage will nonetheless occur at impact speeds of 50 miles an hour. So 30 was a good compromise nonetheless to still determine how ADA systems would react in this in this type of situation. For all the test vehicles that we evaluated, contact was made with the soft car at least 1 out of 3 test runs. Some vehicles performed a little bit better than most or than others, with collisions being avoided, let's say 2 out of 3 times, whereas other test vehicles made contact for all test runs with a minimal amount of speed reduction noted, such as this. The last test that we looked at on the closed course in Momentum was the stop and go functionality of these ADA systems, such as you would see in a traffic jam. That soft car can also be mounted on top of a dynamic platform that can travel up to 50 miles an hour and decelerate with a maximum deceleration of 0.6 Gs. So for this test, we evaluated a number of deceleration rates, including 0.3 Gs, 0.45 Gs, and finally all the way up to 0.6 Gs. The way the test was set up was the ADA system was, or the vehicle with the ADA system was parked approximately 10 feet behind the stationary soft car. The soft car began to accelerate to a steady state speed of 30 miles an hour. And before the soft car started moving, the ADA system was engaged in the test vehicle, so that when the soft car started moving, the ADA system started moving up to match the speed of the lead vehicle with no driver intervention. The soft car was traveling at a steady state speed of 30 miles an hour for about 10 seconds before the decelerations occurred. So we conducted 3 test runs for each of the deceleration rates per test vehicle. So that comes out to 9 total test runs per vehicle. And we were pleased to note that for all deceleration rates, none of the test vehicles made contact with the soft car at any time, regardless of deceleration rate. As a matter of fact, we noted instantaneous deceleration rates exceeding 1 G for some of the test vehicles. So that indicates that these systems are indeed capable of applying a significant amount of braking force to avoid any potential collisions. One of the possible side effects of this, however, is the possibility of rear-end collisions if one of these ADA systems were to brake too abruptly. This particular test, the deceleration that you're about to see was 0.6 G. So that is what you could consider approaching a panic ABS type stop. So moving to naturalistic evaluations, as I previously mentioned, about 4,000 miles were covered for this test, and we noted events as they occurred in the data logging setup that we had. Events could be anything that the test driver deems undesirable, such as a lane departure event, any erratic lane positioning, a failure of the ADA system to slow or stop, and a catch-all category other. So that could be anything that doesn't neatly fall into the previous 3 categories, but is nonetheless undesirable or problematic for the test driver. So between all the test vehicles, we noted a total of 521 events distributed between all the test vehicles. The majority of these events pertain to the lateral placement of the test vehicles, such as a outright lane departure event or erratic lane positioning. So think of like ping-ponging within the travel lane, for example, or getting too close to a vehicle alongside. Because of both the frequency and type of events noted, all test drivers noted some discomfort with use of current ADA systems, and sometimes felt that depending on the roadway, that monitoring the performance of the ADA system was more more intensive than simply just driving themselves. And also because of the frequency and unpredictability of lane centering events, all test drivers did express some level of distrust for each system. With the number of miles covered and the number of events noted among all test vehicles for the roadways traveled, we found on average one event occurred approximately every 8 miles. So here is an example of some deviation from the travel lane for a test vehicle. This was taken on Highway 101, a particularly curvy stretch of the roadway, approximately 100 miles or so north of Los Angeles. This clip, you'll see multiple lane departure or erratic lane positioning events. Before I play the video, you'll note that the lane markers throughout the entirety are pretty well maintained and pretty visible, at least to the naked eye, for this stretch. However, there are, in addition to the curved nature of the roadway, there are some things that could perhaps be giving these systems some difficulty, such as differing pavement types that are encountered, such as a freshly repaved section of roadway that transitions back to the more worn pavement, as well as, let's say, some of these black tar lines in the middle of the travel lane here. So pretty much immediately as the vehicle enters the tunnel, the vehicle deviates completely from the right lane right there, and the driver notes that event with marking it as a lane departure. Here, going back into the sunlight, the vehicle goes onto the right shoulder once again, noted as another lane departure event. And here's what I'm talking about a repaved section of roadway where the color is different from the rest of the roadway. Right there on that transition, the test vehicle deviates once again into the left lane. Here's another resurfaced pavement area. And right here, I think we have another lane departure event coming up in this gradual right curve here. Yes, where the vehicle has difficulty maintaining that curve. Let me see. I think there is no. I think that's it. But as you see, there is a number of events happening here with, let's say, going back into the sunlight, differing pavement, the curved nature of the roadway. All these things possibly play a role with giving these systems difficulty with consistent lane positioning. This particular stretch of roadway was challenging for all test vehicles. All test vehicles exhibited much of the same behavior as you see here. So this is a perfect example of a highway in which that a driver might be better off just driving himself or herself rather than relying on the ADA system to maintain position. The last part of my talk here, I'm going to briefly touch on some noteworthy incidents that have been covered in media relating to the misuse of active driving assistance systems, such as drivers completely disengaging from the task of driving and either playing games on their phone or texting or just completely dozing off in some cases. These types of driver behaviors are not at all appropriate for level 2 systems, because with a level 2 system, as you're aware, a driver is still tasked with the task of driving at all times. A level 2 system is meant to be used with constant driver supervision. And this, I will say that I think that system designers have a particularly challenging role with these with the development and rollout of these systems, because drivers, or humans for that matter, are inherently bad at providing periodic supervision. With these current systems, as I noted, one particular event every 8 miles or so. Well, when these systems get more refined, and let's say that event frequency goes up to one event every 50 miles or every 100 miles, drivers will consequently become less and less engaged in the driving task at hand, and due to tendencies for humans to be poor supervisors of an ongoing process. This type of partial driving automation is particularly challenging because humans are just not good, as I've said, with this type of assistance system. So there needs to be a balance between, let's say, system efficacy versus having a adequate mechanism of driver monitoring integrated within these systems to ensure that drivers are using them as intended. So there are a couple of things that both industry and government agencies could do to, let's say, better educate consumers on the proper use of these systems, as well as develop these systems to take into account HMI aspects. In terms of government stakeholders, for example, discussion of proper use of ADAS systems could maybe be incorporated into driving ed curriculums, and perhaps questions on how to use these systems, and state that they cannot be over-relied on, and that the driver is responsible for driving at all times. These kinds of points could be baked into driver's exams, or both practical roadway exams as well as written exams, as well as, once again, being a significant component of educational materials. For industry, industry could perhaps slow down the rollout of these systems throughout their entire model line in favor of continued development of these systems, both in terms of their efficacy as well as ensuring that there are sufficient driver monitoring mechanisms to make sure that the driver is engaged, and to guide the driver back to being engaged with a driving task through, let's say, escalating alerts, anything from a visual alert on the instrument cluster to an audible alert, muting the stereo, for example, or vibrating the seat to get the driver's attention back on the roadway. And if the driver's attention deviates one too many times on a particular drive, then maybe the system could be disabled entirely for the remainder of that drive. These are all things that stakeholders and various industries can consider with the continued development of these systems. And with that, I will be more than happy to take any questions.
I believe we have a few questions for you, but I'm going to save them towards the end, Matthew. But that was a great presentation. And you talk about consumer over-reliance on the vehicle technology and how it correlates with what's happening in today's world, where everyone's consumed by their technology, whether it's a phone or, the technology that's in its car. So the fact that you brought up, some of the challenges, and then some of the solutions that we can all work together to improve that. So I appreciate that perspective. Thank you.
Thank you.
So we will move on to our next presenter, which is Mike Marshall. Mike is the president of MLM Diagnostics Services out of Hudson, New Hampshire, with a bachelor's degree in mechanical engineering from UMass Lowell. He is an ASE certified master technician with L1 certification. MLM Diagnostics provides diagnostic computer programming and ADAS calibration consultation services for automotive repair shops and collision shops. So with that, Mike, I am going to make you the presenter. and you should be seeing your privileges momentarily. Okay, and with that, the floor is yours.
Thank you very much. So my name is Mike Marshall. As mentioned, I own MLM Diagnostics services out of Hudson, New Hampshire. I do a lot of electrical diagnostic testing, computer programming, and I program a lot of these systems that we're talking about for the ADAS stuff after these cars are in an accident. So I'm going to talk a little bit about these sensors and particularly what is on the vehicles, a little bit about theory and operation, and a little bit about setup, just so you know where they are in the vehicles. ADAS is it's basically a level of automatic driver protection. There's various forms of it, but there's a generic description right there on the slide. Common systems found on a lot of these cars is blind spot system, cross traffic alert system. Those are all in the back. So blind spot would be on the highway if somebody's where you can't see when you're doing a lane change. And cross traffic alert is if you're trying to back out of a parking spot, it uses those same sensors to detect cars coming perpendicular for you. We have 360 camera systems, panoramic view systems, and peripheral camera systems. Those are all parking aids, and what they do is they show a 360 view of the car so you can see if you're going to bump into something when you're pulling into a parking spot. We have sonar parking systems, and we have automatic. I had parallel there, but there's also automatic parking systems too, which will pull you in and out of a parking spot or pull you into a parallel spot. Adaptive cruise, different radar, LiDAR, and camera systems. There's also some older laser systems that don't seem to be used too much anymore. Then you have the autonomous emergency braking. And finally, lane which also overview. Most blind spot systems are set up like this. So quarters of the car underneath the bumper coverage, blind sensors. This happens to be about down to the quarter shown in inside the bumper cover. But that lights up as a vehicle approaches the area, the blind spot area. And the difference between blind spot and cross traffic alert. The upper image shows the detection area of the blind spot sensor, and the bottom shows the detection area of the cross traffic alert. Systems. These systems all require calibration after they're in a wreck. A job that was called to come in and it failed calibration. So when they pulled the bumper off, it's because the sensor was mounted improperly, as seen on the right-hand side. The connectors pointed up in the air. If you look, so after the shop mounted the sensor properly, we were able to go forward with the alignment. On the left-hand side are two images of Toyotas having the radar calibrations performed. You map out and spot, or you map out on the back corner of where the target goes, and Toyota Service Info spells out exactly how to do it. And then there's a procedure that you run in the scan tool for a pass or fail. And if it fails, then you have to go and figure out if there's a component still bent or if the sensor's defective. So the reason these calibrations are done is because a lot of these systems won't turn on warnings if not operational. A lot of times they will just operate, but the spacing won't be right. With blind spot systems, the car will be in the field of view before the light comes on, and there's all sorts of kind of goofy things that happen. Toyota, at least, is one of the ones that will turn on a warning, but sometimes it takes upwards of 6 months. So after a vehicle leaves a repair shop, it can be a returned vehicle because they didn't perform the alignment and it is out of spec. But that's not overly common. There's many times I've been called in and the blind spot sensor is not aimed properly, and the concern is that the light's coming on when the is not in the blind spot. So now we'll move on to parking assist and camera systems. The picture shown is a peripheral camera system calibration done on an Audi. And if you look, the mats in the front here, that's the view out of the front of the car. And then this is the view of the top of the car with all the images superimposed. So there's cameras mounted in the grille, as seen on the image on the right. Also 2 cameras, one on each outside rear view mirror, and then there's one in the trunk. The processing module will compile all that data to give you a superimposed view of the car and the areas around it. The other system that they'll use is the Sonar System, which has sensors in the front and rear bumpers. This system is not always front and rear. Most of the time they're just in the rear, but there are ones in the front. And these sensors are what the computer, the vehicle uses these sensors to help park the car in the self-parking situations. So a lot of the times in the self-parking cars, even these sensors will require some type of calibration. So here's another view of the 360 camera system calibrations that's required. On the left is that Audi that we saw the pictures of earlier. On the center is a Ford Raptor with a 360 system and a backup trailer assist. And on the right-hand side is the Hyundai 360 system. The reason that calibrating these are important is because in the lower left-hand corner is that Hyundai. Before we did the alignments and it had a couple new cameras installed. As you can see, those lines are not clear at all, and the transitions between the front and sides of the cars are really skewed. So on the right-hand side, after the calibration, you can see that the camera views are much better, and it's a lot better, pulling into a spot. The corner views are a lot more transitional. So now we'll talk about adaptive cruise control systems. I know the other guys have touched on it a little bit. ACC is basically, it'll brake the car, and it'll maintain a distance on the car in front of you, basically eliminating driver input for braking and gas. One of them is a windshield camera mounted. Subaru is primarily the only one that does that. They call it their eyesight system. It's all integrated into the lane departure. And a lot of other ones like the Audi, the yellow Audi in the bottom picture, have a radar sensor either behind the emblem or mounted on the front bumper somewhere to detect all this stuff. So again, it has a radar sensor or the stereo camera. I guess I already talked about that stuff. So these are really important to calibrate because these are more of an autonomous type sensor. Almost all of them require some type of calibration after the front end is done. If the alignment isn't done properly, some weird things will happen. There's not many of them out there that will throw a code for misalignment. And also doing it accurately is important because a lot of these measurements are done 10 feet in front of the car, and they want no more than about a half a degree of variance. So if you're out 1 degree at 10 feet in front of the car, at 300 feet, it's going to be significantly more. A lot of these systems, again, they don't throw radar alignment codes. So if it's not aimed right, the customer can pick up the car and have a functioning radar. It will seemingly work. However, when the customer needs it to brake or another task, may not do it correctly. I have been called into a few cars that have had radars not properly aimed. There was no codes and duplicate because you really had to listen to the customer, the details of how they drove it. One of them is most memorable was a Honda Accord, and the shop had slipped up having the radar aimed. The customer took the car and brought it back and said something weird was happening with it and they couldn't describe it. This vehicle had no codes, and when I drove the vehicle, it seemed like everything was okay. However, when I was testing the gap between the car in front of me, the car in front of me got to the left of the roadway to take a left-hand turn, and the car actually accelerated because that car in front of me left the field of view of the radar. The emergency braking as part of the windshield applied the brakes, and there was no accident. But if that didn't happen and the consumer wasn't on their toes, there could have been an accident there. So driving the vehicle in that same position, what I found was if I got to the right car of the roadway and the car in front of me was to the left, the radar would always miss that car in front of me. It would always accelerate, and I could repeat that scenario almost every single time. If the car was centered in the lane and I was centered in the lane, then everything appeared to be okay. The lane and the hand side of the lane, again, everything seemed to be okay. It was just that perfect storm of me being on the right-hand side of the lane and the car in front of me to the left that the vehicle would act up. When I brought it back, what I had found was the radar was bent and aimed to the right-hand side of the roadway. So the shop had replaced the bracket and the radar, and the vehicle then performed properly. But again, there was no codes, there were no symptoms other than what the vehicle driver noted. So now we'll talk a little bit about the lane departure systems and road sign recognitions. The graphic on the left is from the Honda service information, and it talks a little bit about, or it shows a graphic of what happens when a car deviates over a line, and then the steering wheel, the second graph down is the steering wheel control, and then the third one is the shaking of the steering wheel. And it's not uncommon for these cars to cross the yellow line. It's more of an, an aid to keep someone from crossing the line more so than an autonomous vehicle, at least on most of the cars. So this is out of Honda service info again. It talks about what the road departure mitigation, lane departure mitigation, how it works, and how it will shake the steering wheel and beep at you. Basically tell you to road recognition. This is a camera and the reflective capabilities of the signs, and then some of them will decelerate the vehicle to match that speed. If you're on a highway and the speed drops from 65 to 55, it'll reduce the speed of the vehicle. Other ones will just display the road sign on the dash. It'll show general warnings, excuse me, speed limit signs, as well as I'm drawing a blank on the other ones. So when you do a windshield, when you touch the camera, when you dismount it from the vehicle, they all need calibration. Some are dynamic. These are all examples of static calibrations. The left-hand side is a Honda Civic. The center or the left one there with the crosses in the bottom, that's a Subaru Eyesight. The one in the middle is a Hyundai. Then this one here is a Nissan. That's a Toyota, and that's another Nissan. And they all require some type of calibration to be done. And one of the biggest misconceptions in the industry is if we don't unplug the camera, we don't have to calibrate it. And that's wrong, because almost all bits of service info tell you when you replace the glass, when you touch the camera, when you replace the camera, that these calibrations have to be done. And again, this is another type of system that generally will not throw a code unless it is severely misaligned. But most of the time, they just don't operate correctly, and there's no warnings or other signs to tell you they don't operate correctly. So the OEMs are working on these vehicles, and a lot of these sensors, systems are all being tested. The calibration procedures and reliabilities are being used to, improve the vehicles as new technology comes out. So basically, we're all guinea pigs for the OEMs to make sure that these systems work. The goal is to reduce the accidents of these systems, or of these systems to take over driving the vehicle. But a lot of the collision shops that I've worked for think that these systems are just there to make their lives more complicated. So vehicle safety has increased tremendously in a short period of time. Structural designs of the cars, traction control systems, airbag systems, and the ADAS systems all play a part in this. ADAS systems started showing their faces right around the early 2000s, became more mainstream somewhere around 2015. And just about every car I work on now has some type of ADAS system in it. You know, around 2020, 2021s that we're working on the collision shops now, almost every single car has some type of collision control in it. The modern vehicle is very complex and requires highly skilled technicians, training and tooling. That way we can get these systems operational again. ADAS systems require ADAS system and an OEM service info. And they really must be followed because now they can steer, stop, and accelerate the vehicle. These systems are pretty good. They're a pretty amazing technology, but the cameras do struggle to see pedestrians, lines, and signs due to poor illuminations. There is thermal imaging processes that are being tested. There's not many cars that have them, but they're trying to do that more for the pedestrian detection. And a lot of the systems will not do self-tests for the alignment of the sensors. And a lot of my shops, that this stuff is all the predecessor to alignment to fully autonomous cars. So we need to get things correctly, not only for the safety of the consumers, but so that we can prepare when these things do autonomous. And that's all I have.
Mike, that was a great presentation. Thank you. It's interesting to see as, you know, vehicle technology gets more sophisticated, you know, what you guys do on your side of the house in order to keep up with those changes in vehicle technology. And I think from a consumer point of view, we kind of take for granted the amount of work and, you know, research and work that you guys have to do to stay up to that. So I appreciate your presentation. Thank you.
Thank you.
So for now, I'd like to move into our Q&A session. I got a lot of great questions from the audience, and unfortunately, I'm just going to stick with one for each of you, and then hopefully I can send those to you each individually and have you guys follow up on that. So I'm going to go ahead and start by order of appearance, and the first question is going to be for Mike Allen, and this question is there any reduction or increase in traction on these newer marking materials? This is a serious concern for motorcycles with small contact patches.
It's a good question. So can you repeat it one more time?
Sure. Is there any reduction or increase in traction on these newer marking materials? This is a serious concern for motorcycles with small contact patches.
Good question. So there's been a lot of questions in and around markings and their traction. When markings are new and when there's glass beads that just go down on the road, it's very slippery, right? There are different types of materials: paint, thermoplastic, polyurea, epoxy. These are all liquids. And when you add optics to liquids, like you can see in this picture, this is a test panel of a polyurea. Typically what happens is there's extra beads that don't get put into the liquid. And when they don't get put into the liquid, the area is slick. Typically your smaller glass beads are and have a very low BPN, which is an indication of that skid resistance. And then the larger elements that you see on here or preformed tapes have higher BPN. And when a tape that's manufactured in a plant comes out and gets installed on a road, that has a minimum level of BPN that is warranted and applied, that the manufacturer is held accountable to, as opposed to a liquid, which goes out. A contractor drives down the road with a truck. The truck applies the liquid. It applies the glass beads, so it's a little bit harder to monitor the consistency of that skid resistance. So to answer the question, each marking has a different skid resistance. The preformed tapes have higher skid resistance, higher skid ability than some of the pavement marking liquids where glass beads get thrown on after the fact. Does that answer the question?
I'm sorry, I was on mute. Yes,
Yeah,
I believe so. Thank you, Mike. So the next question I'm going to throw to Matthew. Just bear with me while I grab it for you, Matthew. This question, with increasing vehicle automation, are any thoughts being given to drivers becoming less engaged in the driving process and possibly systems that will ensure continuous driver engagement?
So that is a big concern with current active driving assistance systems, because everything available nowadays for consumers is classified as a level 2 system. So as defined, level 2 systems require constant driver supervision, and once again, the driver is responsible for driving at all times. So now there is, among stakeholders in various parts of the industry, a renewed push, if you will, to ensure that driver monitoring systems are designed to pick up any inattention and direct the driver's focus back to the road. As I've mentioned in my presentation, the need for robust driver monitoring systems has been particularly illustrated with numerous incidences that have been covered with drivers misusing these systems to disastrous results. I'm sorry, did that kind of answer the question? Could you repeat that again just to make sure?
With increasing vehicle automation, are any thoughts being given to drivers becoming less engaged in the driving process and possibly systems that will ensure continuous driver engagement? So I believe that did cover the points that she was asking.
Okay, the other thing I want to add to that real quick is, as previously mentioned by other panelists, these current systems can be looked at as perhaps building blocks, if you will, to more autonomous systems. So as we increase to eventually level 3 and 4, for example, that will become less of a concern because level 3 systems, the driver is not responsible for driving within the OOD, ODD of that system, and then level 4, it becomes less of an issue because within the ODD, the system is able to account for all situations, including the possible inclusion of a limp home mode to account for any system failures or whatnot.
Perfect. Thank you, Matthew. And I believe this question goes to Mike Marshall. Mike, these systems seem helpful. How do we get drivers to understand the ADAS is not autonomous driver tools?
A good question. I think it really just boils down to as much public input as we can about these systems and operations. And it may boil down to when the consumer picks up the car from the dealership or whoever's selling it to them, that they really emphasize it and put a lot of stress on it. I don't work very often with the vehicle owner. Most of my interactions are with the shops. So a lot of that stuff that I deal with is just the aimings and the importance of aimings and proper services of these systems, more so than trying to get the consumers on board with understanding how they operate.
Okay, thank you. And I believe this question is for all of you, if you'd like to answer this. Do you all believe that 100% autonomous vehicles will happen in differing style vehicles? And I guess, Mike, we'll start with you.
Yeah, I do. I think the time frame for autonomous vehicles is still probably some years out now, but they're working on the technologies and the trainings and making sure that servicing these cars and the importance of servicing these cars is all being built on right now. So everything that we're doing now and all the technologies we have now is only going to be built on it in the future. And it's only going to be more important as time goes on to make sure that these procedures are done properly.
Mike Allen, Matthew, do you guys want to weigh in?
I will say that I think that full vehicle automation is something in the future. Probably my honest opinion, and this is just my own words, I think that this is still decades out into the future, because this is a monumental undertaking, because not only do significant advances in deep learning and artificial intelligence have to be complete for full autonomy, but in addition to the vehicle, there's also the infrastructure challenges that go with automating roadways and vehicles as well.
Sure. Thank you. Mike, I'll give you the last word.
Sure, I agree with both Matt and Mike. I think, ultimately we are, the industry was going full bore, before COVID, and then COVID obviously slowed everything else down. It's slowing this down. So like Mike said, I mean, we're seeing different manufacturers of cars at different levels. Look at that. Look at what Audi's doing. Look what Tesla's doing. Very innovative. And then you have other manufacturers. They're kind of all accelerating at different speeds. So while they're looking at all these technologies, you're seeing it. It's not consistent, and it's going to take some time. I think with the new MUTCD that's being reviewed right now, it's going to be interesting to see what components the federal government is going to recommend that are, connected to ADAS technology and autonomous technology. But I think it's going to be a slow go. I don't think it's going to be quite as fast as maybe it would have been had COVID not hit.
Interesting perspective. Thank you. Unfortunately, that's all the time that we have. I wish we could get to more of the questions that we received, but I'll definitely send those along to our panelists and possibly have them reach out to each of you. We will also have these presentations available on our website and on our YouTube channel. You can find us at NH Office of Highway Safety. I'd love to thank the panelists today for sharing their expertise and knowledge with us. It's not often that we get to talk about vehicle technology, and it's interesting to see it kind of come full circle. We start with Mike Allen talking about what 3M's doing as far as pavement markings and how those pavement markings help out with what Matthew's doing as far as research and machine vision systems. And then on the other end with Mike Marshall and how he and his team are on the back end looking at all of those different types of technology and coming up with ways to keep up with what's happening in the industry. So thank you all for your time. I appreciate it. Before I let all of you go, I'd like to introduce the Commander of Highway Safety, Captain Bill Haynes. He's going to close out our traffic safety session.
Good afternoon, everyone, and thank you, Jen, for allowing me to take a minute to speak to everybody. I want to really spend out a special thanks to our presenters today. I also want to make sure I thank both Jen, Chelsea, and Dan for putting this all together. It's been truly a pleasure to watch these as they've been presented. I also want to thank all of our partners, because without partners and our partnerships, we would not be able to be successful. So thanks to all of you for being on this call today. As you all know, one of the challenges to highway safety is two-pronged. One is behaviorally and the other is infrastructure. Today talked a lot about either infrastructure and automation in vehicles, using that infrastructure, and we work each and every day from the NHTSA and the Office of Highway Safety perspective of dealing with that in a behavioral nature. Tying these two together is critical as we move forward to our success. More importantly, the types of partners on this call today are extremely important and to all of us. We have anywhere from highway safety professionals, we have Federal Highway, we have National Highway Traffic Safety Administration, we've also got driver educators and police officers, and all of you are our partners, and we genuinely value what you do each and every day and how you support us in achieving our goals to reduce crashes. By reducing crashes, we reduce not only serious bodily injuries, but more important, useless fatalities that occur in our roadways. One of the topics you had today is near and dear to my heart. It had to do with aging drivers. Obviously, nighttime has become an issue for a lot of us, and we've talked a little bit today about some of those impacts, not having the proper markings on the infrastructure, and how some of these automated devices could help prevent some of that as long as it can be recognized. So thank you for that. Again, I don't want to take too much time here today. I'm just extremely happy to see all of you on this call today and appreciative to all that you do each and every day for us. And if there's anything any of us here at the Office of Highway Safety can do for you in the future, please reach out to us directly, and we'd be more than glad to do anything we can to achieve all of our goals. Thank you very much. Have a happy and prosperous new year.
Thank you, Captain Haynes, and thank you all for joining us today. Have a great weekend and enjoy.
Thank you.
Thank you, Jennifer.
Thank you.